Okay. So previously, we studied so-called the epsilon and delta argument on the limit of functions. All right. And using that, so we were able to define the meaning of a function being continuous at a single point C. Okay, and today we have three different functions, f, g, and h, and they are tending to L1, L2, and L3. In this case, the limit behaves very well under addition, multiplication, and division. So, well, this one tending to L1, L2. This one is tending to L1 and L times L2. And well, as long as L3 is a non-zero number, and this is also tending to L1 over L2. Proof is very important. But yeah, I really want because we are still slightly running behind the schedule. So okay, please allow me to skip the proof of this, and let us take this for granted. For those of you who are interested, and yeah, you can read it. And we have another theorem about the squeeze theorem. This is very much similar to the squeeze theorem in the sequence. All right, we have three functions, f, g, and h. And all these functions are the functions defined on an open interval containing C, possibly except at x equals to C. Okay, I mean, since we are talking about the limit, so we are only interested in the neighborhood of C, not the point C itself. Okay, anyway, we have these three functions, and these three functions will satisfy these inequalities on this open interval. And if the left function and the right function, if they are both tending to the same limit, then the middle function is also tending to the same limit. So this is the squeeze theorem. Okay, I believe this is the very nice exercise to prove this. Okay, so we have to limit as x is tending to C, f of x and h of x, they are tending to the same number, say L. Okay, so using the epsilon and delta argument, this means for any positive real number epsilon, so I can find a real number, say delta 1, such that if x differs from C by less than delta, then fx minus L is less than epsilon. Yeah, I can find such a nice delta 1. And likewise, for the same epsilon, we can find another real number, which I will call delta 2. And if x minus C is less than delta 2, then h of x minus L is also less than epsilon. You can find such a nice delta 1 and delta 2. Okay, now what? Now I am supposed to show that g of x is tending to L. So for this epsilon, if I can find such a nice delta, then we are done. Then what would my delta be? I want to choose my delta to be minimum between delta 1 and delta 2. Because if x minus c is less than this delta, if x minus c is less than this delta, then that means x minus c is both less than delta 1 and delta 2 at the same time. Therefore, I can make use of these two inequalities at the same time. Right? So then L minus epsilon, yeah, I will rephrase these inequalities like this. The function value, f, lies between L minus epsilon and L plus epsilon. And the function value, h of x, is also lies between L minus epsilon and L plus epsilon, right? Okay. And on top of that, we also know that these three functions are satisfying these two inequalities. So L minus L, which is less than f of x, which is less than equals to g of x, less than equals to h of x, and this is still less than L plus epsilon. Okay, because of this. All right. So L minus epsilon is less than g of x, less than L plus epsilon. So in other words, g of x minus L is less than epsilon. Okay. All right. So for any epsilon, we could find a delta. And if the difference between x and c, so if x differs by c less than delta, then the function value of gx minus L, they differ less than epsilon. So in other words, g of x is tending to L as x is tending to c. Okay. Good. Okay. All right. We also have these theorems. Well, f, g, and h, if they are all continuous at this point, and well, then f plus g, fg, and f of g, they are all continuous at the same point. H of c is non-zero. How do you prove this? Well, proof of this, okay, you have to remember that there is a alternative definition of the continuous of functions using the limit. And since this limit behaves very well under addition, multiplication, and division, therefore, by the same nature, f plus g, f times g, f over g, they are all continuous at the same point. So theorem 2.3 should be considered as an automatic consequence from theorem 2.1. So therefore, the proof is also be omitted. Okay. All right. And some variations. The first one is the left and right limit. I guess from time to time, you have seen these kind of symbols. Well, instead, well, x is tending to c, but we have one additional plus sign over here and one minus sign over there. So intuitively, so this implies, well, so this is called the right limit of function f. So intuitively, so you're trying to find the limit of function as x is approaching to c from the right. So that is what I mean by the right limit. And likewise, this one. So this one is you're looking for the limit of function as x is approaching to c from the left. Okay. So this is very but as we did before, so I would like to provide you very rigorous definitions of these two things. So what is the definition of left-hand limit and right limit? These are defined like this. For every epsilon, you must be able to find a positive real number delta satisfying if these definitions look pretty much very similar to the previous definitions of continuous of function at C. But the only difference is well, previously we are interested in the behavior of function here. So this is what. So we are talking about the deleted neighborhood of C. So say that this is point C, and if this is the length of delta, then we are talking about the the behavior of the function at near the delta neighborhood of C, right? This or that. But in this case, we are not talking about the delta neighborhood. We are only interested in the right interval, right delta neighborhood of C. So this is and likewise, this is for this definition, we are only interested in the behavior function when x is the left delta neighborhood of C. Yeah. No. Not good. Right? Yeah. Sorry. Yeah. Okay. So and this is the definitions of the left and right limit. And you may remember that from time to time I talked like so as x is blowing up to the positive or negative infinity. See, I talked that, so I use that expression a lot. But what is the precise meaning of f is going to plus or minus infinity? So we still need to talk about that. F of x is getting positive infinity. This is defined like this. For any positive real number m, you must be able to find a number delta, positive real number delta, such that if x differs by c less than delta, then fx is greater than m. Well, okay. Hey, so why have I changed the symbol from epsilon to m? Well, because by the conventions from the mathematicians, the epsilon usually refers to the very small number, but m usually refers to the very large number. So you may try to understand this like that. Just choose any large number. So m, well, say that m is 1 million. Then that means, but you can still find the delta, and for this delta neighborhood of C, the function value is greater than 1 million. So, and you have to remember that M was chosen arbitrarily large number. Therefore, that means if you're getting really close to the delta neighborhood of C, then your function value can be arbitrarily larger than any large number that you can ever imagine. So this is the meaning of the F is getting arbitrarily large. So yeah. I want to draw a little picture of this. This is the, I should say this is the vertical asymptote. vertical asymptote가 뭐냐? 점근선. 그쵸, 점근선. All right. So in this picture, suppose that this is my M. Then how close my X to C so that function value is greater than this guy? Well, the answer is very simple. So if my X is close to C by this much, then I'm pretty sure that my function value is greater than this one. Okay. So in this case, for this M, my delta would be, which one is shorter? Yeah, I guess this is shorter. Yeah, my delta should be a distance from this point to that point. Okay. But however, as I increase my delta M, as I increase my M, but then the delta should be also, typically delta should be also decreasing, right? So, so in this case, the distance from this point to that point, yeah, I know this is so tiny small. Which one is shorter? Yeah, in this case, I guess this guy is even shorter than this. So this distance would be my delta, right? So, therefore, if X is close to C by less than this delta, then I know that my function value is greater than this one. Right? Here, the point is, for every possible real number M, you can still find the delta. And this implies that f of X is going to positive infinity. And you can try to define almost the same thing for f is tending to negative infinity. Do you think you can give a definition of f is getting to negative infinity as X is approaching to C? Yeah, I guess you can easily do that. Yeah. Can I show this? Well, of course, f of X is just 1 over X squared. Now I'm looking for the under what condition my function is greater than positive real number n. And this is the same as X is greater than, sorry, less than. X should be less than 1 over square root of n, right? So for any positive real number m, so I want to choose my delta to be just 1 over square root of m. Then f of X which is 1 over x squared. Sorry. Oh, I messed up. Yeah. I forgot to say that if the distance from x to the origin is less than this delta, then f of x, which is 1 over x squared, but since x squared is less than delta, so this one, it should be less than, greater than delta squared, right? Yeah, because we are taking the reciprocal of this, so we have this, and this is 1 over m. So which is, so for if x is close to 0, less than delta, then the function value is greater than m. So proof is done. Okay. Okay, good. Okay, please allow me to go to the next page because, yeah, we are now in the next section. 2.2b about continuity on an interval. All right. So far, so we have been discussing the definition of a function being continuous at a single point C. So that now we can do that. We can easily do that by using epsilon delta argument. And today we're going to talk about a function being not only continuous at a single point, but continuous at whole entire interval. This interval might be some open interval, open and bounded interval, or closed and bounded interval, or the interval from maybe from negative infinity to positive infinity. Also, all those intervals. Okay, for such intervals, your function is defined, and we're going to talk about what is the meaning of function being continuous on this whole interval. If you're supposing you're a mathematician and you're trying to give a definition of your function being continuous on the interval, not a single point. And how would you do that? The first definition that comes to my mind is, I want to define that if my function is continuous at every single point on that interval, then maybe I can say my function is, I can define my function is continuous on the interval. That could be my definition, right? Yeah, this is very fine. This is very okay definition, not bad, but we can do even more. Yeah, today I'm going to introduce you slightly stronger definition of function being continuous on interval. So which is called the uniform continuous. All right. Okay. All right. Okay. The uniformly continuous, we say function is uniformly continuous on an interval. So uniform continuous can only be told on not only a point, but an interval. We say function is uniformly continuous on an interval. Okay, now here goes the definition. For any positive real number epsilon, you must be able to find another positive real number delta satisfying this blah 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 condition. And okay, what is the blah 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 condition? Such that you choose 2 points x and z in interval I. So these 2 points must be in the interval I, and they are differ by less than delta. So this means the absolute value of x minus z is less than delta. Then the difference between these two function values, fx and f of z, they differ by less than epsilon. If you can find such a nice delta for every single possible real number epsilon, then we say the function is uniformly continuous. Okay. Well, it looks very much like to the continuous on a on a single point. What is the difference? Before I do that, so let me rephrase this definition by using quantifiers. For every epsilon, there is a possible real number delta such that if x and z are in the interval and x minus z absolute value less than delta, then f of x minus f of z is less than epsilon. This part is somehow different from the previous definition. Okay, so if you do not remember, for your information, so this is the definition of f being continuous at a single point. This is defined to be for any epsilon, there is a delta if x minus z is less than delta. Sorry. See, then f of x minus f of z is less than epsilon. Now, the difference between this definition and that definition is even clearer to me. Well, okay, for this definition, and what was the range of x? What was the range of x? X, well, the point C is fixed, and this is the fixed point, right? And we are only interested in the function values on the delta neighborhood of C, right? If the function values for the axis in the delta neighborhood of C, if the function value is less or satisfy this inequality, then we are good. But in this case, we are talking about not on the delta neighborhood of some very special fixed point, but we are talking about just any pair of points in I, and if they are, as long as they are close to each other by less than delta, then this inequality must be satisfied, right? So I mean the position of x and z, they are like they are not they do not matter. As long as they are close to each other by less than delta, then they must satisfy this inequality. Well, so therefore, if we can find such a delta, then we say f is uniformly continuous. So which one do you think is more stronger condition? This or that? Yeah, uniformly continuous is much stronger condition compared to the just continuous at a single point. Why? Because here all you need to do is just check the delta neighborhood of C. That's it. But in order to check if any given function is uniformly continuous, then you are supposed to check every pair of points in interval I that is close to each other by less than delta. Right? Right? Yeah. If you do understand the difference between this and that, then I think you're 90% done in today's lecture. Okay, so for those of you who do not understand, well, most of you, yeah, I will provide you an example. Mm. Okay. Say that this is the graph of y equals to f of x, and this is my interval I. And I want to I want to see if this function on this interval is uniformly continuous or not. To check that, in order to see that, first I will need to choose any arbitrary epsilon and see that if I can find such a nice delta. Okay. So. Just consider, say that this length of this line segment is my epsilon. And can I find such a nice delta? Okay. Based on this picture, so it looks like if my pair of points x and z are in this range, then the function values they differ by less than epsilon. So I am really tempted to say that, length of this line segment would be my delta. Am I right? No, not exactly, because, say that this is my x, and this is my z. Yeah, even though, okay, then the length of this line segment is my delta. But this delta does not work for any such a pair of points because yeah, I know this is getting a little bit tedious. Yeah, sorry about that. Yeah, but separated by this delta does not guarantee the difference of the function value is less than epsilon, right? Because if your delta for those 2 points, and in order to be proper delta, then this condition must be satisfied no matter, okay, as long as these 2 points are less than delta. In this case, if you set this length of this line segment to be your delta, then these 2 points are they are less than delta, but their function values are clearly, difference between their function values are clearly greater than epsilon, right? So, so now I can see that, in this case, for this much of epsilon, my choice of delta would be even much smaller than this guy. I mean, it looks like the length of my delta would be even smaller than the length of this line sigma. Okay. So for this epsilon, is it my proper delta? No, not exactly. Because, sorry. If is, well, in this case, no. This delta is still not small enough because for these 2 points, x and z, they differ by less than delta, but their function values are still greater than epsilon, right? So what would my delta be? My delta would be, well, at least smaller than the length of this line segment. Okay. Now, and okay, so I'm really tempted to say that length of this line segment is my delta for this epsilon. Am I right? Yeah, in this case, finally, I'm good. So this is the proper delta. So therefore, for this epsilon, my delta must be at least smaller than length of this line segment. Then for this delta, and if my x and z is less than this delta, then the difference between the difference of the function values is known to be less than epsilon. So this is going to be my delta. Okay. And all right, this time around, what if I choose even smaller epsilon? For the smaller epsilon, by using the same trick, I can still find the delta satisfying this condition. So in this case, yeah, well, even though this is not, well, precise mathematical argument, but according to this picture, maybe I can say for any epsilon, you can find such a nice delta satisfying this condition. Okay. I mean, this is my rule of thumb, but you can find your delta on where the slope of your graph is the greatest. So try to find your delta on the point where the slope of your graph is greatest. Then that is going to be the smallest possible delta you're looking. Okay, but anyway, this is, well, you can find such a nice delta for every epsilon. So this function is uniformly continuous. So this is f is uniformly continuous on interval I. Okay. And well, this is a non-example. No. This is the graph of y is f of x. And my interval is this. This is the interval. And I want to find out if this function is uniformly continuous on the interval I or not. And I guess you understand this notation. Well, this is the parenthesis and this is the bracket. So this means this side of interval, this point is excluded, but this endpoint is included. So this is, sometimes we say this is half open interval. Okay, and in this case, let me try to find the delta for this epsilon. Okay, based on this picture, it looks like the length of this line segment would be the delta for corresponding to this epsilon, but actually it isn't. Why? Because, because this is X and this is Z. Because 2 points differ by less than this delta does not guarantee the function values are differ by less than the epsilon. Because, well, here, this length is even smaller than this one, right? So therefore, and this X and Z, even though they are differ by less than epsilon, so less than delta, but their function values differ by even greater than this epsilon, right? So therefore, it looks like, maybe if I choose the length of this line segment to be my new delta, then maybe that would be good. But no, it isn't. Because, let me magnify a little bit more. If you're getting more and more close to the origin, this is this and this is that. Do you see the length of this line segment is even smaller than the previous one? So this small delta does not suffice to satisfy the inequality. Okay, but so this time around, let me say the length of this tiny little segment is my new delta. But this delta would not be enough to satisfy the inequality because as you're getting more and more close to the origin, then function values, they differ by greater than or equals to epsilon. Right? Okay, so that means for this epsilon, you can never be able to find such a nice delta. Because, as you're getting closer and closer and closer to the origin, then the difference between the function values is still greater than or equals to epsilon. So in this, therefore, your function is not uniformly continuous on this interval. F is not uniformly continuous on I. I really like this example because this example tells us the difference between just continuous on every single point on interval I versus uniformly continuous on the interval I. Okay, so let me go back to this picture. This is very nice interval, right? And on this interval, the graph looks like very continuous. So in this function on this interval, I can say this function is continuous everywhere on the point on every point in the interval I. Yeah, that is very nice. That is true proposition. So, however, even though the function is continuous everywhere on this point, but this function fails to be uniformly continuous on interval. Right? Yeah. Okay. Time for some examples. I have some easy function. F of x is x squared. And I want to show that this function is uniformly continuous. Sorry. Uniformly continuous on the interval from 0 to 1. All right. The preliminary analysis. First, I want to find under what condition the difference between the two function values is less than epsilon. So f of x minus f of z, this is the difference of the function values, which is x squared minus z squared. And this is, factoring this out, x minus z and times x plus z. And I'm looking for some kind of upper bound of this one. Bound. So how do I find this one? It looks like if I can show that this guy is bounded by less than some constant multiple of absolute value of x minus z, then I guess we are good. But there is one condition. These 2 points, x and z, must be the point in this interval. Therefore, x and z, these 2 points, they are at most what? They are at most 1, right? So this factor, second factor, absolute value of x plus z, must be bounded by 2. So this is 2 times absolute value of x minus z, and we want that this guy to be less than epsilon. So, therefore, our delta should be less than, delta must be epsilon over 2. Right? Okay. Good. Okay. Time for a proof. For any epsilon, I let delta to be epsilon over 2. Then for any 2 pair of points in this interval, and if they are close to each other by less than delta, then the differences of the function values which is less than 2 times x minus z, but this is still less than 2 times delta, which is just epsilon. Okay. So independent from the position of choice of x and z, as long as they are close to each other by less than delta, then the difference of the function values is guaranteed to be less than epsilon. So my function f on this interval is uniformly continuous. Right? Yeah. 여러분 지금 잘 따라오고 계신가요? 네, 괜찮아요? 영어로 강의를 하면은 여러분과 저 사이 약간 좀 배리어가 생기는 것 같은 느낌이 드는데 괜찮아요? 여기까지. 이거 사실 너무 쉽죠? 막 따라 할 수 있죠? 막 이런 얘기 계속 이런 식의 얘기를 하고 있는데 실제로 전혀 쉬운 내용 아니거든요. 그러니까 옆에 친구들은 다 고개 끄덕끄덕하고 나만 모르겠어 이렇게 생각하지 마시고요. 사실 거의 대부분 모르고 있다 보시면 돼요. 괜찮아요? 그러니까 아직 일단 그럼 계속 나가 볼게요. 네. 자, 오케이. Now this example is my favorite, one of my favorite. I have a function, 1 over x. And I am supposed to show that this function is not uniformly continuous on the interval from half open interval from 0 to 1. Well, obviously, 0 cannot be included in this domain of this function because 1 over dividing by 0 is prohibited. Okay. Okay. In order to show any given function is not uniformly continuous, then, well, as we did before, so I will try to find the negation of the statement. So what is the negation of a statement? So, in order to show the function is not uniformly continuous, I'll just copy and paste. So you take a negation of this. So that means there is an epsilon. And for this epsilon, no matter how small your delta is, but you can still find 2 points on the interval, and these 2 points are close to each other by less than delta, but fx minus f of z is still greater than equals to epsilon. If you can find one such epsilon, then that proves that your function is not uniformly continuous. Okay, and for this epsilon, and no matter how small your delta is, not every pair of points x and z, but you must be still able to find these 2 points. They are close to each other by this much, but their function value difference of the function value is greater than this. If you can find, and you should be able to always find these pair of points from your interval. Then this proves your function is not uniformly continuous. Okay, so let me try to find such a bad epsilon. In this case, I will set epsilon equals to 1 is the bad epsilon that we're looking for. Then we choose any delta, any positive delta. Okay, now suddenly, somehow, for some mysterious reason, I will try to find a positive real number no, so positive integer such that n squared plus 3 times n plus 2 is greater than 1 over delta. Hey, what is this? Well, typically delta is very small number. No matter, because, well, I always say no matter how small your delta is. So delta is very small number. Therefore, 1 over delta usually be very large number, large and positive number. But however, the point is, well, no matter how large your right-hand side, right-hand side is, but you can still find a integer satisfying this inequality. Yeah? Yeah. Okay. So there is such an integer. And now we let x is 1 over n plus 1 and y, sorry, not y. Yeah, I should be saying z. Z is 1 over n plus 2. Then both of these numbers, they belong to the interval I. Right? Now, and so the distance between x and z, which is 1 over n plus 1 minus 1 over n plus 2. This is the like denominator things. Yeah. N plus 1, n plus 2, and is 1. Yeah, everything is positive numbers, so yeah, I'm good too. Okay, and this is factoring out, so expanding this, n squared plus 3n plus 2. And this is less than delta. Okay. Okay, so here, what I'm trying is this. Well, for any delta, I could find 2 points from the interval, and the x and y, they are close to each other by less than delta. But f of x minus f of z, which is the function f is just 1 over x, so f of x should be just absolute value of 1 over n, 1 plus n plus 1, and f of z is just n plus 2, right? And this is 1. And this is clearly greater than epsilon, because my epsilon was 1. Okay, so what I'm doing here is this. So for this epsilon, no matter how small your delta is, but I can still find 2 points, x and z, from the interval, and they are less than delta, but the difference of the function values is still greater than this number. And this proves that function is not uniformly continuous on the interval. Okay, yes. And this example is very, the function, this function, f of x is 1 over x, even though this function is continuous at every single point on this to be uniformly continuous. So I want to compare these two definitions, being continuous everywhere and uniformly continuous. So if f is uniformly continuous on the interval I, then f is continuous at every point in proof is clear. See, because, well, f being uniformly continuous on I means as long as they are close to each other by less than delta, then their function values are less than equal. The difference of the function value is less than epsilon. So what you have to do is once you change this z by just a fixed point, say c, then if x is close to c by the less than delta, then the function value at x and minus function value at c is less than epsilon. And this is precisely the definition that f is continuous at the point c. Therefore, if f is uniformly continuous, then f is continuous everywhere. However, the converse of the statement is not true because of the previous exercise. Right? Yeah. Okay. So we have studied the how uniformly continuous is even stronger condition than it's continuous everywhere. But if we impose one additional condition towards this interval I, then suddenly the converse is true. That is, if your interval I is a closed and bounded interval, then f is continuous everywhere suddenly implies f is uniformly continuous. If f is continuous everywhere on this closed and bounded interval, then f is uniformly continuous on this closed and bounded interval. I will prove this. The proof of this is slightly complicated, uses slightly complicated argument, but I'll try my best, follow one by one. Okay, proof by contradiction. Suppose not. F is not uniformly continuous. So that means there is, okay, try to remember the negation of being uniformly continuous. There is a positive real epsilon, and such that for this epsilon, then no matter how small your delta is, then you can find those 2 points, x and z, in the interval I, and such that the difference of the function value is still greater than or equals to epsilon 0. And since you can find all such x and z's for any delta, so for this time, I will just focus on the case when delta is 1 over n. N is a positive real integer, positive integer. And for this delta, you can still find 2 points, x and z, satisfying x minus z is less than delta, and f of x minus f of z is greater than or equals to epsilon 0. For this delta, you must be able to find 2 such points. Well, and yeah, I'm going to give them a name. So, and for every integer n, you can find these 2 points. So I'm going to give them a name. So I will say this is xn and yn, zn. And yeah, maybe I'm okay to replace this by just one of them. Okay. So, okay, so that means we have infinitely many xn's and infinitely many zn's. So we have two sequences, xn and zn. Their sequences in this closed and bounded interval a and b. Okay, now I'm gonna take advantage of the previous lemma. So do you remember this? Well, for every infinite sequences, you can find monotone subsequence from it. So by that lemma, there is a monotone subsequence x and k of xn. So this is a subsequence of monotone subsequence of xn. And since the original sequence is bounded sequence, therefore this sequence must be a converging sequence because of the monotone convergence theorem. Is converging to a point in A, B. Okay, and now you have to remember that xn minus zn is less than 1 over n. So these subsequences x and k, and for this subsequence, choosing a subsequence means choosing a subset of indices of n, subset of indices. Therefore, for these indices, and for xnk minus znk, they must be less than 1 over nk. But this is still 1 over n, k is, so this is the 1 over nk means the kth term of this subsequence. But this nk means it should be always less than equals to k. So nk is always greater than equals to k. Therefore, we have this input. Okay, so we have two subsequences, so x and k and z and k. But in order not to mess up the indices, we have to rearrange the index. Rearranging the indices. We write x and k is just, from now on, I will just call x and k is just xk, and z and k is going to be zk. And xk minus zk is less than 1 over k. And well, because of the construction of the sequences, so this is still greater than equals to epsilon 0. Okay, so we just ended up with two subsequences from this original sequence. Now, this time around, I'm going to apply the same lemma to this new sequence, zk. Then we can obtain the subsequence from this sequence. So, well, here, you're taking the subsequence of the subsequence. But we can still do that because this is, even though this is a subsequence, but this is still infinite sequence. So by applying the same lemma, just one more time, there is a monotone subsequence, which we call, ZKL of ZL. ZK. And by the way, so this new subsequence is also convergent. And X and L minus Z and L is, well, less than 1 over L. Sorry, should be K. Is less than KL, but this is still less than 1 over L. So KL is XL and KL is ZL, and XL minus ZL is less than equals to 1 over L, and XL and YL, they still greater than equals to epsilon 0. Okay. So, so this sequence XL is still, well, I need to emphasize that this subsequence, XL is the subsequence of this sequence. XL is still a subsequence of subsequence, but since this sequence was known to be converging to a point, therefore, this subsequence of any converging sequence should be also converging to the same number, right? So this is a converging sequence, and this is another converging sequence. So we were able to derive a converging subsequences from the original sequence X and Y. So we have two converging sequences, XL and ZL. And because of this inequality, XL minus 1 over L is less than equals to ZL, but this is also XL plus 1 over L, right? So, and by the squeeze theorem, as L to the infinity, the limit of Xn and the limit of ZL must be the same. So which we will call C. And this is clear also a point in the interval A and B. So, and F is continuous. Everywhere. So F is continuous at C, which is the limiting point, which is the limit of these two sequences. And since F is continuous, the converging sequence is also converging after composition. So F of XL f of ZL, they both converging to f of Z because f is continuous. And this is contradiction. Why? Because, well, we have this inequality. Because of the constructions of these two sequences, these new composed sequences, they cannot close to each other less than epsilon 0, right? The difference between these two sequences must be at least epsilon 0, but it says they are tending to the same number. So I believe this is a contradiction. Okay. So this is the problem. All right, yeah. Sorry, this is for today, and see you next time.